Between two heartbeats of the universe, there is silence. It is not the silence of space, nor of death, but of something deeper, the absence of movement itself. The stillness before the next instant dares to arrive. Imagine a world where time has paused, not slowed, not fractured, but ceased to remember its own direction. A drop of rain hangs forever above the ground. The ripples below never forming, a dying star remains eternally on the edge of collapse, its light caught mid-flight across the void. Every sound, every breath, every vibration held in a single unending shimmer of existence. In this impossible stillness, physics begins to tremble, for every law, every equation, every rhythm of life assumes one quiet truth: that time moves. But what if it didn't? What if the very current that carries galaxies across billions of years simply stopped flowing? The second law of thermodynamics, Einstein's relativity, quantum mechanics, all whisper in different languages about time's passage, yet none can explain why it must pass at all if time can stretch, bend, and slow. If it can stop at the edge of a black hole's event horizon, then could it also forget to move forward entirely? In that frozen instant, would light still exist? Would space still expand? Or would the universe remain? Perfectly preserved, a sculpture of eternity carved in motionless fire. This is not fantasy. It is the shadow physics cannot ignore. For beneath every ticking clock lies a quiet fear that time itself might one day hesitate and never begin again. In the beginning, there was no before and after. There was only everything, compressed into a single incandescent instant. A universe smaller than an atom, silent and infinite at once. And then something irreversible happened. Not merely an explosion of space and energy, but the birth of direction itself. A flow that would carry stars, galaxies, and living minds across the unfolding tapestry of existence. That first unfolding was not only the origin of the cosmos, it was the birth of time's arrow. For time, as it is known, is not a simple rhythm. It is the quiet current beneath every heartbeat, every orbit, every decay. It is not made of particles or waves, yet it rules them all. And though its flow feels inevitable, the universe hides a strange confession within its mathematics. There is no rule demanding that time must move forward. The first humans who pondered the heavens did not know this. To them, time was a circle, the eternal return of seasons, tides, and stars. In ancient Greece, Aristotle imagined it as the measure of change, a clock woven into motion itself. He believed it had no true beginning or end, only cycles, the slow heartbeat of the cosmos. For nearly 2,000 years that idea endured. But in the 17th century, Isaac Newton broke the circle. In his mind's universe, time was absolute, a river that flowed at a steady pace, untouched by anything it carried. It existed independently, ticking with divine precision whether the stars moved or not. Absolute, true, and mathematical time, Newton wrote, flows equably without relation to anything external. In his equations, every second was the same everywhere, from London to the farthest nebula. Space and time were distinct, immutable, and eternal. The stage on which creation played its scenes, never altered by the actors. It was a comforting image, an anchor for a mechanical world, but it was wrong. 3 centuries later, that steady river shattered. In 1905, a young clerk in a Swiss patent office wrote words that changed the shape of reality itself. Albert Einstein proposed that time was not a passive backdrop, but part of a living fabric, space-time. In this fabric, time could bend, slow, and stretch depending on speed and gravity. Clocks would disagree. Seconds could stretch into centuries near the grip of immense mass. And yet, buried within Einstein's equations was a disturbing symmetry. The laws of physics, written so elegantly, made no distinction between past and future. A falling stone, a collapsing star, a decaying atom. Every equation could run backward as easily as forward, and the universe would remain mathematically valid. If the laws of physics did not demand direction, then where did the arrow come from? For a long time, the answer seemed buried in mystery. Einstein's relativity described the shape of time, but not its flow. Quantum mechanics later described the behavior of matter and energy. Yet its equations too were timeless, indifferent to before and after. To the universe, time seemed not to move, but to exist all at once, as a vast static landscape, every event, every moment, coexisting in the frozen geometry of space-time. And yet, here on Earth, the arrow feels absolute. A candle burns, ash cannot become wax again. A life moves forward and never returns. Entropy grows, and memory records only what has been, never what will be. The universe seems to agree with this direction, even if its fundamental laws do not. The key was hidden in something mundane and profound, the tendency of order to crumble into disorder. In the 19th century, physicists studying steam engines stumbled upon a principle that would become one of the most powerful ideas in science. They called it entropy. It began as a way to describe inefficiency, how heat spreads, how energy degrades, how no machine can ever be perfectly reversible. But entropy was more than waste. It was the measure of how disordered a system becomes as it evolves. In the language of thermodynamics, entropy always increases, and from that simple rule, the arrow of time emerges. Every time heat spreads, every time energy diffuses, every time a system moves from order to chaos, the universe takes one more step forward in time. The reason the past feels different from the future, the reason the two cannot be swapped, is that entropy has already grown. A glass shatters but never reassembles. Smoke disperses but never returns to the flame. Stars collapse into black holes but never spontaneously. Reform.entropy gives direction to existence, but the arrow's origins run deeper still, all the way back to the beginning. The early universe was astonishingly ordered. Moments after the Big Bang, matter and radiation were spread out in a nearly perfect, low entropy state. This simplicity, this improbable calm, was the seed of time's forward march. Had the universe begun in chaos, time might never have taken a direction at all. In a high entropy cosmos, every moment would be statistically indistinguishable from the next. There would be no before, no after, no unfolding. Entropy began low, and from that imbalance, time's arrow was born. As galaxies formed, as stars ignited and died, as life arose to measure change, the universe continued its long drift from order into disorder. The expansion of space itself stretched energy thinner, creating an asymmetry that would make forward progress inevitable. Each atom's motion, each collapse of a dying star, each thought inside a human brain, all are consequences of that original gradient of entropy. Time is not a fundamental law of the universe. It is a consequence of the universe's initial imperfection. Yet this explanation brings a haunting realization. If the arrow of time was born from the low entropy of the Big Bang, then it is not eternal. One day, when entropy reaches its maximum, when stars burn out, when energy is evenly distributed, when nothing more can happen, time itself will lose its meaning. The universe will no longer have a reason to move forward. In physics, this is known as heat death, the final equilibrium of existence. In that far future, the arrow will fade, and every event will become indistinguishable from every other. No memory, no motion, no before or after, only a cosmic stillness, vast and eternal. The arrow of time, then, is not law. It is memory. Memory is the echo of a symmetry. When a system changes, it leaves behind traces of what it once was. Fossils of causality embedded in the fabric of space. Every photograph, every atom displaced, every pattern preserved is an imprint of that movement forward. Without memory, the difference between past and future would dissolve. A universe without record would be timeless. This connection between entropy and memory runs deep into the nature of consciousness itself. The human brain, like the cosmos, stores information by increasing entropy, rearranging molecular structures, converting energy into heat as it forms patterns. Each act of remembering is, in essence, a physical act of disorder. The mind, then, is not just a witness to time's arrow. It is built from it. Every thought is a fragment of entropy growing, an echo of the universe expanding. And yet, not all physicists are satisfied with this explanation. Some argue that entropy alone cannot fully explain why time moves forward everywhere, universally, in every corner of space-time. Relativity teaches that time flows differently for each observer. Quantum mechanics shows that at microscopic scales, processes can appear reversible. Particles can entangle, oscillate, and even tunnel backward through what seems to be time. If the universe is a single four-dimensional structure, a block universe, as some call it, then all events may already exist, eternally frozen within that space-time geometry. In such a cosmos, there is no now sweeping forward. Past, present, and future coexist. Our perception of motion through them may simply be the illusion of consciousness experiencing its own trajectory. The arrow, in this interpretation, is not an objective flow. It is the feeling of movement through an already completed map. To us, that map feels alive because we are moving through it. To the universe, nothing moves at all. Still, something in the equations resists timelessness. Though relativity treats time as dimension and quantum mechanics permits reversibility, the universe's large-scale behavior defies perfect symmetry. Radioactive decay always moves one way. Black holes evaporate but never reassemble. Entropy increases, not by chance, but by statistical necessity. The arrow persists. Even in the most extreme conditions, near event horizons, inside quantum fields, across the cold, dark sea between galaxies, time continues its forward drift. It may not be a law, but it is, for now, a fate. The story of time's arrow is not only about physics, but about fragility. It reveals that direction itself, the sense of unfolding, of causation, of life moving toward the unknown, depends on an ancient imbalance at the dawn of creation. If that imbalance had not existed, there would be no stars, no entropy gradients to drive complexity, no flow of energy to power thought. The universe would have been a stillborn symmetry, perfect, motionless, eternal, and utterly lifeless. What we call time's forward march is the slow unraveling of that perfection. The arrow is both destruction and creation, the decay that allows life to emerge. Every living system fights entropy locally, consuming order to maintain its fragile existence against the greater tide of disorder. And yet even that struggle obeys the arrow. Every breath, every heartbeat, every synapse firing contributes to entropy's growth. The living universe is a candle burning at both ends, creating beauty from its own dissolution. So what then is time? Perhaps not a substance, but a relationship. A way the universe organizes its own change. Perhaps not a line, but a gradient, from what was simple toward what is complex, or perhaps not movement at all, but memory, the structure that remains when order forgets itself. The arrow was born when the universe chose a symmetry, and one day, when that imbalance fades into perfect stillness again, the arrow will vanish. Time will no longer forget or remember. It will simply cease to be. Until then, the universe continues its long fall from order to chaos, carrying with it every burning star, every collapsing wave, every fleeting human thought. The flow is irreversible not because the laws demand it, but because the cosmos still remembers how to move. For now, the arrow remains unbroken, pointing forward, carved into the silence between two eternal seconds. It began with a simple thought: what if time does not beat the same for everyone? In the quiet year of 1905, a young patent clerk sat in the glow of a Swiss afternoon, his desk cluttered with the dreams of other inventors. Outside, trams drifted along cobbled streets, their wheels humming the rhythm of ordinary hours. But inside Albert Einstein's mind, the ticking of clocks was coming apart. He imagined two lightning bolts striking a moving train, one at the front, one at the back. To a man standing on the platform, the flashes seemed simultaneous. To a passenger aboard the train, one strike appeared before the other. Each was right. Each lived in a different time. In that moment, the universe split its symmetry. Time, once thought absolute, dissolved into something pliable, relative, dependent, alive. Einstein's insight shattered the last illusion of Newton's eternal clock. The cosmos no longer ticked together. It breathed. It warped. It bent under the weight of motion and gravity. And from that revelation, everything changed. In Einstein's new cosmos, space and time were not separate threads. They were woven together into a single, trembling fabric, space-time. Where mass gathered, this fabric curved. Where speed increased, the rhythm of time itself slowed. A clock on a mountaintop would run faster than one in the valley below. A spacecraft nearing the speed of light would see centuries pass outside, while its own seconds trickled by. This was no poetic metaphor. It was measurable, physical truth. Time could stretch. Time could shrink. But Einstein's discovery carried a quiet terror beneath its elegance. If time could bend, could it also stop? In 1971, the question left the blackboard and entered the sky. Physicists Joseph Haffel and Richard Keating loaded 4 atomic clocks onto commercial airliners and sent them circling the Earth, once eastward, once westward. Atomic clocks, precise to billionths of a second, are humanity's most perfect measure of time. When the planes returned, the readings disagreed. Clocks that had traveled east, in the direction of Earth's rotation, lagged behind their stationary twins. Clocks that traveled west ticked ahead. The difference was minute, only a few hundred nanoseconds, but it was real. Time had curved. The experiment confirmed what relativity had predicted. Motion and gravity distort the flow of time. Every orbit, every rotation, every acceleration reshapes the rhythm of existence. Even the GPS satellites that guide ships, planes, and phones must correct for this distortion. Without relativistic adjustment, the system would drift by kilometers each day. Every direction humanity navigates through space is quietly dependent on Einstein's broken clock. And yet, for all its accuracy, relativity whispered a paradox deeper than any clock could measure. Its equations did not distinguish between past and future. They worked perfectly in reverse. In the fabric of space-time, every moment, every birth, every death, every flicker of a photon exists eternally as part of a vast, unchanging structure. This vision came to be known as the block universe. To the block universe, time is not a river. It is a frozen landscape, a 4-dimensional sculpture where the entire history of the cosmos exists simultaneously. The Big Bang, the present, and the end of all things are already there, carved into the same immutable whole. Nothing moves. Nothing becomes, everything is. In this frozen geometry, change itself becomes illusion. The movement of a planet around a star, the pulse of a heartbeat, even the feeling of passing seconds, all are patterns inscribed into the static fabric of space-time. What humans perceive as motion is not the universe changing, but consciousness sliding through different coordinates of that unchanging map. The sensation of time flowing is like a spotlight sweeping across a completed painting, illuminating each brushstroke in turn. The painting does not move. Only the light does, but the light too may be an illusion, a story told by minds evolved to experience sequence, not simultaneity. If Einstein's clock truly broke, it did not stop ticking. It revealed that there was never any ticking at all. The implications unsettled even those who loved the theory. Einstein himself resisted the idea of true passage. In a letter written near the end of his life, he comforted the family of his lifelong friend Michel Bessot with a strange serenity. "Michel has left this strange world a little ahead of me," he wrote, "but it means nothing. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." To him, the block universe was not a nightmare. It was peace. No event is ever truly lost. Every moment, from the birth of stars to the flicker of human thought, remains forever inscribed in the cosmic architecture. But to others, this vision was unbearable. If everything already exists, where is choice? Where is change? Where is life's becoming? Physicists and philosophers wrestled with the paradox. If relativity's space-time is a solid block, why do humans experience its surface as a flowing stream? One explanation looked inward, to the structure of consciousness itself. The brain, bound by entropy and causality, can only record and recall information in one direction. Memory is irreversible. It can remember the past, but not the future, because the processes that encode memory increase entropy. In this view, the arrow of time is not a feature of space-time, but of the observer. The universe may be timeless, but minds are not. To a timeless cosmos, every moment is equally real. To a living observer, each new moment feels born from the last. The flow of time, then, might be the mind's interpretation of its own trajectory through a static universe, a translation of geometry into story. And yet, Einstein's vision still resists full comprehension. Quantum mechanics, born only decades after relativity, seems to rebel against the frozen block. In the quantum realm, particles exist as probabilities, waves of potential that only choose a state when observed. Each measurement seems to carve one branch of reality from a cloud of possibilities, forcing time to advance. If all outcomes exist simultaneously in a timeless structure, why does observation collapse them into one? The block universe leaves no room for uncertainty, yet quantum physics thrives on it. Perhaps the block itself is not perfectly solid. Perhaps it trembles at the smallest scales, flickering with indeterminacy. A crystalline structure in which the quantum threads of reality weave their own uncertain futures. At cosmic scales, time bends under gravity. At quantum scales, it seems to dissolve into probability. Between them lies the domain of the observer, the bridge between physics and perception. Here, the broken clock becomes more than a symbol of relativity. It becomes a mirror of existence itself. In regions of intense gravity, near black holes, time slows to near stillness. A clock dropped toward an event horizon appears to freeze, its final tick never reaching the outside world. To an external observer, the clock never crosses the boundary. To the clock itself, time continues, and it falls inward without end. Einstein's theory predicted this paradox long before black holes were confirmed. It showed that time is not uniform. It is a fabric that stretches until it tears. And when it tears, the meaning of before and after collapses. In the heart of relativity, there is a quiet symmetry. It allows time to flow backward or forward, yet human experience insists on one direction. It predicts a timeless block, yet consciousness feels motion. The contradiction is not a flaw in physics. It is the mirror where reality reflects itself. The block universe offers a haunting perspective that everything humans will ever do, every civilization that will rise or fall, already exists in space-time's architecture. History is not unfolding, it is being read. Perhaps this is why relativity feels both liberating and terrifying. It grants eternity, but takes away becoming. The future is not waiting to happen. It is already there, woven beside the past, silent and unchanging. And yet, even in a frozen cosmos, something profound remains. A being trapped within the block cannot see its totality. It can only experience its own narrow path through it. That path, the journey through the illusion of time, is what gives meaning to existence. Without it, there would be no story, no motion, no memory, no wonder. The block universe may hold all moments at once, but awareness transforms them into experience. Consciousness, perhaps, is the way the timeless universe becomes aware of its own geometry, one moment at a time. Einstein's clock did not break by accident. It revealed that the ticking was never in the machinery of the world, but in the perception of those who measure it. A century after that quiet revolution, modern physics continues to chase the fracture. Experiments on entangled particles show that information can connect across space and time, as if both were mere illusions. Quantum gravity theories, from loop quantum cosmology to string theory, suggest that space-time itself may be emergent, a pattern rising from something deeper and more abstract. If that is true, then time too is not fundamental. It is born from the relationships between things, not their existence. The block may not be ultimate. It may be a projection of a deeper order where before and after are meaningless. In that deeper realm, Einstein's broken clock might find its final stillness, not because it failed, but because it reached the end of what clocks can describe. In the cold mathematics of relativity, there is no flowing river, only coordinates, but between those coordinates lies the miracle of perception. If all moments coexist, then every heartbeat, every word, every flicker of light has always been and will always be. The universe, in its silence, holds them all, immutable and eternal. What humans call the passing of time may simply be the act of remembering eternity, one frame at a time. And so, the day Einstein's clock broke was not the day time ended. It was the day the universe revealed that it never truly began. In the language of physics, entropy was meant to be the arrow that never faltered, the quiet law ensuring that time would always march in one direction. From order to disorder, from the spark of beginnings to the ashes of endings. But beneath its certainty, something began to whisper, a rebellion so slow, so subtle, that even the ticking of the cosmos could not immediately hear it. The second law of thermodynamics was humanity's first glimpse into time's true heartbeat. Clausius wrote it in the 19th century, long before the universe was known to expand, long before anyone had seen a black hole or traced the cosmic microwave background. He had observed something simple. Heat does not flow backward. A cup of tea cools on a cold morning, but never warms itself. Disorder increases. Systems spread their energy until balance, stillness, is achieved. From this quiet truth, time's arrow was born. Entropy became its compass, its reason to move forward. But the deeper physicists looked, the more fragile that compass appeared to be. In the 20th century, a young physicist named Ludwig Boltzmann peered into the atomic heart of this law. He realized that entropy was not a force, not a mystical tide, but a count, the number of ways the atoms of a system could arrange themselves. Disorder, in its truest form, was probability. A state of order, a pristine crystal, a newborn universe, is rare. Disorder, the scattering of molecules, the collapse into equilibrium, is common. Time flows from the rare to the probable, from the precise to the inevitable. But Boltzmann's insight contained an unease he could never fully escape. If the arrow of time emerges from probability, then on a long enough scale, even improbability must happen again. Given infinite time, the universe could rearrange itself back into order. By chance, the arrow would bend, and entropy, the great storyteller of forward motion, would momentarily forget its tale. This was the first hint that entropy's power might not be absolute, that the arrow could, under the right cosmic conditions, dissolve into stillness. As the 20th century deepened, new eyes began to stare at the universe's birth and death, and entropy was found there. At both ends, watching silently, Roger Penrose, the geometer of space-time, asked a question that pierced through the elegance of the laws. Why was the universe's beginning so ordered? If entropy drives time forward, then the Big Bang, the moment from which all time began, must have been an extraordinary state of low entropy, a perfect balance poised on the edge of chaos. Everything that has unfolded since, the stars, the galaxies, the minds that ponder them, has been the consequence of that initial asymmetry. Penrose saw that the Big Bang was not just an explosion of matter and energy, but of order itself. The gravitational field was smooth, almost eerily so. The cosmos began not as a storm, but as a perfect calm waiting to decay. Entropy gave time its arrow, but the arrow was lit only because the universe began improbably still. Stephen Hawking, following this path, took entropy to the edge of darkness, to black holes. There, at the boundaries of no return, entropy swelled to unimaginable heights. The more massive a black hole, the greater its entropy. This, Hawking realized, meant that even in the heart of gravity's abyss, the second law held. The universe was still obeying its ancient rhythm, from low entropy to high, from smoothness to decay. Yet the paradox that haunted Penrose lingered. Why did the universe begin in such perfection? If entropy always increases, what prepared the low entropy beginning that allowed the increase to exist at all? No one could answer. The arrow of time seemed born from a condition it could never explain, an origin that physics could describe, but not justify. As the cosmos ages, entropy's grip tightens. Stars burn through their nuclear hearts, scattering photons into the dark. Galaxies drift apart, their collisions slowing, their lights dimming. Black holes devour what remains, hoarding entropy like cosmic accountants of decay. In time, unthinkable spans of it, the stars will die, the night sky will go empty, white dwarfs will fade to black, neutron stars will cool, and even black holes, through Hawking radiation, will evaporate into the background silence. This is the heat death, the great equilibrium, the moment when the universe has exhausted all gradients of difference. No heat, no energy, no motion, no before, no after. In this final stillness, entropy reaches its maximum, and when everything is the same, time itself loses meaning. For time is not a separate thread, it is the measure of change, and where no change can occur, there is no time to measure. The rebellion begins not in defiance, but in silence. Entropy, the law that gave time its direction, completes its work, and in doing so, erases the very need for direction at all. The arrow of time, triumphant through eons, dissolves in the symmetry of nothing left to change. Yet physics, ever restless, has refused to let the story end here. Quantum theory introduces uncertainty, flickers of possibility that never fully settle, even in the deepest stillness. Vacuum fluctuations, virtual particles, the shimmering of empty space, they all hint that absolute equilibrium might be impossible. Even the void hums with energy, restless beneath the surface. Some cosmologists propose that from this quantum restlessness, new beginnings might arise, small regions of low entropy, birthing new universes in an endless cosmic cycle. Penrose called this conformal cyclic cosmology. The idea that the far future of one universe could become the Big Bang of another, entropy reborn as order, the arrow beginning again. Others imagine quantum tunneling events, fluctuations so vast they inflate a new cosmos, a new direction, a new river of time. But these are speculations, dreams suspended at the edge of mathematics. The observable truth remains. The universe, as seen today, is cooling, fading, expanding into isolation. Entropy continues to rise, and the arrow continues to thin. In this light, entropy's rebellion is not a revolt against physics, but a revelation of it. It reveals that time's direction is not an inherent law. It is a condition, a temporary asymmetry born from an ordered past. It reminds us that everything familiar, life, thought, memory, depends on imbalance, on gradients, on the difference between before and after. If the universe ever reaches a state where every atom, every photon, every piece of information is evenly spread, then the future will cease to be distinguishable from the past. The concept of next will lose meaning. To an observer, if any could exist, it would seem that the cosmos had gone perfectly still, every moment identical to the last, every fluctuation averaged into silence, a universe that has forgotten motion, and yet within that silence lies a profound symmetry, a peace beyond tragedy. The universe, having scattered all its energy, would have found its final equilibrium, the state it has always been moving toward. Time's rebellion would not be an act of destruction, but of completion. Entropy's rise was never a march toward chaos, but toward balance. The universe does not die screaming. It exhales softly into the dark. Every atom that once burned in a star, every photon that once struck a retina, every memory that once defined a mind, all become part of the same quiet tapestry, woven without motion, without end. Time's arrow, having carried existence across billions of years, finally sets itself down, not broken, but fulfilled. And in that frozen eternity, where entropy has silenced the difference between past and future, the question returns. Did time end, or did it finally remember what it always was? For perhaps time was never meant to move forward at all. Perhaps its motion was only the echo of our perception, a fragile construct of creatures living between the expansion and the silence. And when the final symmetry arrives, it will not be time that stops. It will be the illusion of direction that fades. The cosmos, in perfect stillness, will not mourn, it will rest, as it always has, in the quiet where no second dares to follow another. In the deep silence of the quantum world, symmetry reigns like an ancient law of nature. For every action, there should be an equal reflection. Every particle should have its mirror twin, every motion a mirrored reverse. To the mathematicians of the early 20th century, this symmetry was sacred. It spoke of balance, of order, of a universe elegant enough to repeat itself both forward and backward in time. But the universe, it seems, is a master of quiet betrayals. In the 1960s, in a laboratory buried beneath the hum of American power lines and the pulse of Cold War ambition, physicists performed an experiment so delicate it would shatter that ancient belief forever. They studied the behavior of a rare particle, the neutral kaon, a ghostly fragment born in high-energy collisions, living only a fraction of a second before decaying into lighter matter. Under the rules of symmetry, the kaon's decay should look identical whether time moves forward or backward, whether matter or antimatter takes the stage. But what the detectors revealed defied expectation. The kaons, when left to the judgment of time, did not behave as their mirror selves were meant to. There was a difference. Faint, almost imperceptible, but unmistakable. The laws of physics, for the first time in recorded history, had whispered a bias. This moment, known now as CP violation, marked the first fracture in the perfect mirror of time. C for charge, P for parity. Two symmetries that, when joined, were believed to preserve the universe's fairness between matter and antimatter, between the forward and the backward. But nature had quietly chosen sides. Before this discovery, physicists had believed in the deep impartiality of reality. Every process that could unfold in one direction could, in principle, unfold in reverse. A glass could unbreak, a flame could pull its smoke back into the candle, a planet could unwind its orbit. If only one could reverse the flow of time itself. This was the dream of symmetry, a vision of a cosmos where direction is illusion, where forward and backward are two faces of the same coin. But CP violation revealed that the coin was marked. It began with the weak nuclear force, one of the four fundamental interactions that govern the universe. While gravity shapes the stars and electromagnetism binds atoms, the weak force governs the transformations of subatomic particles. The subtle alchemy where one form of matter decays into another. In this invisible theater, particles and antiparticles are expected to dance as perfect opposites. But the neutral kaon, when examined, betrayed an unexpected asymmetry. Its decay favored one configuration slightly more than the other, as if time itself leaned gently toward the future, nudging events to unfold in one particular order. It was as though the universe had a preferred story, one direction of the real that could play, but not its reversal. The discovery sent shockwaves through physics. It was made by James Cronin and Val Fitch in 1964 at Brookhaven National Laboratory, and it earned them the Nobel Prize. But the deeper implications were almost too vast to comprehend. For if the laws of physics are not identical when time is reversed, then perhaps the arrow of time is not merely a macroscopic illusion born of entropy. Perhaps it is written into the smallest equations of the universe itself, encoded in the language of quantum decay, hidden in the trembling of invisible fields. The symmetry had cracked, and through that crack, existence itself seemed to shine. For the universe is built on a delicate rivalry, matter versus antimatter. When the Big Bang erupted from its singular origin, it should have produced equal parts of both. Each particle of matter should have had an antiparticle twin, identical in mass, opposite in charge, destined to collide and annihilate in a flash of radiation. If symmetry had been perfect, no atoms, no stars, no life could have survived. The universe would have been pure light, bright, brief, and empty. But it wasn't. For every billion antiparticles, there was one extra particle of matter, a tiny imbalance, a whisper of imperfection. And that whisper became everything. Every planet, every star, every cell, every thought, all born from the fraction of matter that symmetry forgot. It is believed that CP violation, this subtle preference for one decay path over its mirror, is what tipped the scales. The universe chose matter. It chose asymmetry. And from that choice came permanence. The laws of physics, then, are not perfect. They lean, ever so slightly, toward existence. This quiet tilt is the reason the cosmos did not dissolve into annihilation. In the decades after Cronin and Fitch's experiment, physicists sought to uncover the deeper roots of this cosmic bias. At CERN, at Fermilab, at Japan's KEK accelerator, beams of particles were smashed together with increasing precision. They found that the effect was not limited to kaons. It appeared in beam mesons too. Each time, nature chose a side, breaking the mirror anew. It was as though, in the subatomic heart of reality, time had chosen to remember, a faint, almost moral inclination, toward forwardness, toward unfolding. The standard model of particle physics could describe these violations, but not explain them. The mechanism was encoded in the CKM matrix, a set of mathematical parameters describing how quarks, the building blocks of protons and neutrons, transform into one another. But why those parameters took their values, why the universe should favor one direction of decay, one dominance of matter that remains a mystery. Some suspect a deeper layer of physics beyond the standard model, a realm of new symmetries yet undiscovered, where CP violation is not an accident, but a clue. Others imagine that the violation is not a flaw, but a signature, the quantum fingerprint of time's irreversibility itself. The implications ripple far beyond particle physics. For if the universe's matter exists only because symmetry broke, then time itself may exist for the same reason. The forward motion of everything, from decaying atoms to dying stars, maybe the echo of a decision made in those first trembling moments after the Big Bang. When time broke symmetry, it created history. It created causality, the simple, sacred sequence of cause and effect that defines experience. Before that break, perhaps there was no before, no after, only an eternal quantum haze, balanced between all possibilities. And in the instant symmetry failed, reality began to remember its past. But what if one day that preference fades? What if, at the deepest levels of nature, the imbalance that gave us being begins to even out again? If CP violation were ever to vanish, if the weak force ceased its bias, matter and antimatter would again stand equal. The very distinction between future and past might blur. In such a universe, motion could persist, but direction would lose meaning. Events might unfold not toward a future, but simply exist, simultaneous, eternal, undecided. This speculative thought rests on the edge of science, yet it is rooted in possibility. For symmetry has a way of restoring itself. The cosmos began in balance, broke it to exist, and may one day return to that perfect stillness where no side can win. The ultimate equilibrium, not of energy, but of time. In the faint glow of distant galaxies, the legacy of that broken symmetry still burns. Every photon emitted by a star, every atom fused in its core, every chemical reaction that sustains a living being, all depend on that microscopic bias. Without it, no carbon would exist to bind the molecules of life. No gravity would pull matter into suns. No consciousness would ever have wondered why the universe remembers moving forward. And so, when physicists speak of CP violation, they speak not only of particles and decay, but of the origin of meaning itself. The reason something exists rather than nothing. The reason events unfold rather than remain still. In the symmetry that failed, time found its motion. And in that motion, reality found its story. The day Einstein's space-time folded into quantum mechanics, the dream of a timeless, perfectly mirrored universe began to fracture. Now, at the smallest scales of matter, we glimpse the imperfection that gave birth to time's flow. The cosmos is not the clean geometry once imagined by mathematicians. It is a living asymmetry, a pulse of imbalance that keeps existence from collapsing into stillness. Perhaps time is not an arrow, nor a river, nor a line at all. Perhaps it is a consequence, a shadow cast by broken symmetry, a memory of imperfection etched into the quantum fabric of the real. And when the universe has cooled, when entropy has smoothed every fluctuation, when black holes have sighed their last radiation into the dark, the bias that made us may fade back into the silence that preceded it. The mirrors will align. Matter and antimatter will dissolve into light. The arrow will fold in on itself, and time, having broken its symmetry once, may return to its origin, not as motion, but as stillness beyond memory. In that stillness, the universe will not end. It will simply stop preferring, and the story that began with a broken mirror will close in the perfection of balance, the place where forward and backward are one, and time once again forgets to move. In a laboratory bathed in the pale blue hum of lasers, the air seems to hold its breath. Here, time does not rush. It is coaxed, measured, and almost persuaded to stop. Every photon, every atom, becomes a fragment of something ancient and immense. The human desire to know what lies beneath motion itself. Physicists have long tried to chase time to its vanishing edge, to peel away its illusions, to corner it where the seconds falter. In rooms colder than any winter on Earth, they have slowed light to a crawl, letting it move not at 300,000 kilometers per second, but at the pace of a bicycle ride. Inside superconductors, electrons glide without friction, tracing loops of motion that seem eternal. And within clouds of ultra-cold atoms, suspended just a few billionths of a degree above absolute zero, the familiar pulse of entropy fades almost completely. Here, at the threshold of nothingness, a new kind of experiment begins, one that no clock can properly follow. In 2012, at Harvard and MIT, a strange whisper emerged from theory into experiment: the time crystal. First proposed by Nobel laureate Frank Wilczek, the idea seemed almost impossible. A crystal in space, a diamond, a salt grain, a snowflake, repeats its structure across distance. But what if a crystal could repeat across time? What if, even in its lowest energy state, when all motion should stop, something inside continued to oscillate, forever repeating its own rhythm? It sounded like an act of defiance against the second law of thermodynamics. Yet, a decade later, physicists witnessed that defiance come alive. At Google's quantum computing lab, researchers lined up a chain of 20 qubits, quantum bits made from trapped ions. Using the Sycamore quantum processor, they pulsed these particles with precise microwave patterns. The system fell into a rhythm, flipping back and forth again and again, without consuming energy, without decay. Like a pendulum that refused to slow, a heartbeat with no metabolism. They had not stopped time, but they had created a pocket of it, a loop that ignored the arrow. What emerged was not perpetual motion in the classical sense. It was something more subtle and perhaps more profound. In a normal crystal, symmetry is broken in space. Its atoms form repeating patterns, turning smooth emptiness into ordered shape. In a time crystal, the symmetry is broken in time. It exists in a rhythm that should not exist, an unprovoked pulse in a world that should have gone still. And in this rhythmic defiance lies something fundamental, a glimpse of time's dual nature. For in physics, time is not motion. Time is the relation between motions. Remove all change and time itself becomes meaningless. But what if a system could keep changing, even when nothing around it does? Then perhaps time is not a universal river at all, but a property of matter itself, emerging only where matter dances. Some physicists have come to see these time crystals, not as curiosities, but as a new phase of matter, one that forces a revision of what it means to exist in time. Yet not everyone agrees. To some, these oscillations are illusions born of careful control, the result of periodic driving, not true defiance. The system is not escaping time's arrow, they argue. It is being led through it, choreographed by the laser pulses that created it. But even so, something profound is being whispered through these experiments, something that may reach far beyond the lab. Because if time can crystallize, if it can repeat itself, not endlessly forward but cyclically, like breath, then perhaps the universe itself contains such hidden patterns. Across cosmology, hints of recurrence are everywhere. Roger Penrose's conformal cyclic cosmology imagines that the universe, after expanding to near emptiness, could one day begin again, not through explosion, but through the quiet erasure of difference. When all particles become massless, time loses scale, and the dying cosmos blends seamlessly into a new Big Bang. One aeon gives birth to another, not through destruction, but through symmetry restored. On quantum scales, similar ideas shimmer in equations. Physicists like Julian Barber have long proposed that time itself is not a flowing entity, but an illusion, the emergent appearance of change in a timeless landscape of possibilities. In Barber's model, every configuration of the universe already exists, past, present, and future, as static frames in a vast cosmic mosaic. What we call motion is merely the human mind sliding across them, finding continuity where none truly exists. If these ideas are right, then the time crystal is not just a technological curiosity. It is a signpost, a shimmering glimpse of how the universe itself may hold its pattern, even when nothing moves. At temperatures near absolute zero, atoms begin to lose their individuality. Their quantum waves overlap, merging into a single collective state, known as a Bose-Einstein condensate. Within such a cloud, distinctions blur between one atom and another, between rest and motion, between now and then. It is here, in these silent condensates, that physicists have observed behaviors that stretch imagination. Light can be stored, literally stopped, as information imprinted in the stillness of atoms. Quantum interference patterns can persist for seconds, minutes, timescales unthinkable in the chaotic warmth of the everyday world. To stop a clock, one does not need to halt its hands, only to remove the difference between moments. In ultra-cold matter, those differences vanish. And so, in a quiet chamber beneath layers of vacuum and magnetic shielding, humanity has built its smallest imitation of eternity. But experiments are never just about results. They are philosophical instruments, mirrors that reflect how we define reality itself. The time crystal has become such a mirror. It forces physicists to confront one of the most difficult questions in all of science. Is time a fundamental ingredient of the universe, or merely a description of how things change? If it is fundamental, then time crystals are paradoxes, cracks in the laws that govern existence. But if time is emergent, then these experiments may be revealing its birthplace. In the quantum world, no universal clock ticks, Particles obey probabilities, not timelines. A quantum system evolves through its wave function, an abstract shape that exists outside conventional time. When observed, it collapses into an instant. Between these collapses, there is no before or after, only superposition. This means that deep down, nature may not experience time the way we do. What we call the flow of time might simply be our translation of quantum evolution into human experience, a story told by matter as it rearranges itself. The search for a time crystal, then, is not just an engineering feat. It is a meditation on existence. When researchers switch on their lasers and cool their atoms, they are not merely manipulating matter, they are pressing their hands against the fabric of duration itself. They are asking whether motion is possible without cause, whether repetition can exist without time. If the answer is yes, then the universe may be far stranger than any clock suggests. In a distant future, when the stars fade and the last black holes evaporate, the cosmos will cool toward equilibrium. Entropy will flatten every difference. Temperature, density, and energy will become uniform. Change will cease. In that final stillness, perhaps only patterns like time crystals will endure. Microcosmic echoes of motion without progress, order without flow. A pendulum swinging in eternity's void. To some theorists, this is the ultimate symmetry. The restoration of balance between forward and backward, between before and after. A universe that once expanded and burned, returning at last to perfect quiet. Yet within that quiet, faint ripples remain. Self-repeating structures, flickering even when nothing remains to measure them. Perhaps that is the final irony, that in its death, the universe might still remember rhythm. But there is another possibility. Some physicists, studying quantum information, believe that time may not stop even then, that the correlations between particles, the entanglements that stretch across space-time, will persist. Though no new energy flows, the universe will still compute, reshaping its own information endlessly, like a vast, cold algorithm running without observer or intent. If that is true, then the death of motion is not the death of time, only the death of heat, of light, of memory. The computation continues, invisible, imperceptible, recursive. The time crystal, in this view, is a microcosm of eternity's endurance, not a defiance of time, but a proof that its essence is not flow but recurrence. The experiment that stopped a clock did not end the story of time. It opened its smallest door. Behind it lies a question older than physics itself, a question that predates the first tick of any clock. What is motion, if not the remembering of stillness? What is time, if not the universe learning to move again? In the faint hum of superconductors, in the frozen breath of ultra-cold atoms, in the repeating pulse of a time crystal, humanity has heard something ancient. Not the silence after time ends, but the echo that began it. For as long as matter finds rhythm, as long as even one pattern repeats, the universe will never truly stop. It will shimmer, quietly, endlessly, at the edge of eternity. In the great silence between galaxies, where the light of 1 trillion suns has thinned to near nothing, the universe holds a memory of everything that ever was. Every photon that left a star, every ripple in space-time from a dying black hole, every whisper of temperature in the cosmic microwave background, all are traces, imperfect records of events long past, and perhaps it is in these traces that time itself is born. For over a century, physics has tried to reconcile two faces of the cosmos, one curved and continuous, the other granular and uncertain. In Einstein's relativity, time is a woven dimension, bound to space, stretched and bent by gravity. It is smooth and geometric, a clock that ticks differently for each observer depending on how deep they are within space-time's fabric. But in the strange mathematics of quantum mechanics, time begins to dissolve. The equations that describe subatomic particles do not require a ticking second hand. They speak in probabilities, amplitudes, and wave functions, none of which need a direction. A quantum state simply is. Only when measured, when something is remembered, does it appear to have evolved at all. And here lies a haunting suggestion, that time is not fundamental to reality. It may be a side effect, a consequence of the universe remembering its own changes. Carlo Rovelli, one of the leading voices in quantum gravity, has proposed a radical way to think of time, not as an absolute stage on which events unfold, but as a pattern of relationships between things. In his relational quantum mechanics, Time is not something that exists everywhere, for everyone. It is local, emergent, and deeply tied to information. The universe, in this view, does not contain a single master clock. Instead, every system, from an atom to a galaxy, keeps its own form of time, derived from how it interacts, exchanges information, and remembers. The flow we experience is not universal. It is relational, stitched from the imperfect exchange of knowledge between matter and energy. Where there is correlation, there is direction. Where information changes, time moves. Imagine two particles, born together and then flung apart. They remain entangled, quantum twins sharing an invisible bond. Measure one, and the other changes instantly, even across light years. But if neither is measured, if no information is exchanged, then no evolution occurs. Between them, time has no meaning. Time, then, may not be an independent river flowing past all things, but a fragile current created whenever systems interact. It emerges from memory, from the way one part of the universe keeps imperfect track of another. This imperfectness is crucial. Perfect information would mean perfect symmetry, and in a perfectly symmetric universe, there would be no before or after, no entropy, no story to tell. The universe must forget, just enough for time to exist. Entropy, once thought to be a measure of disorder, can now be understood as a measure of lost information. When a cup of coffee cools, it is not chaos that increases, it is uncertainty. The microscopic details of heat exchange are lost to the vast number of interactions too complex to trace. In that loss, time finds its direction. If the universe could remember everything perfectly, if every atom carried a flawless account of every collision, every photon, every vibration, then entropy would never rise. The arrow of time would vanish. It is the blurring of memory that allows time to move forward. From this perspective, the universe is not so much aging as it is forgetting. The Big Bang was an explosion not of matter, but of memory potential. A moment of near-perfect order, where almost everything was known and predictable. As expansion began, that clarity fractured. Information spread out, collided, entangled, and was lost. Time, as we experience it, is the long echo of that loss. The deeper the universe falls into forgetfulness, the faster time seems to flow. But one day, when the last stars burn out, when black holes evaporate, and when every quantum state reaches equilibrium, no more information will change. Entropy will have reached its maximum. The cosmic memory will be full and yet paradoxically empty, because nothing new can be written upon it. That will be the day when time itself fades away. In this distant future, the heat death of the universe, nothing will remain to record difference. Photons will stretch to infinite wavelengths, losing their identity. The fabric of space-time will flatten, stripped of curvature, stripped of motion, and without difference. There will be no before or after. No observer will mark a moment. No particle will exchange information. No fluctuation will disturb the stillness. In that perfect silence, the universe will not die. It will complete itself. For time's purpose was always to carry imperfection toward equilibrium. When balance is reached, the story ends not in tragedy, but in stillness. Time does not shatter. It simply becomes unnecessary. Yet some theories hint that the story might continue, not with clocks and calendars, but with memory itself reawakening in another form. In certain cosmological models, information can never truly vanish. Even when entropy reaches its peak, the correlations between quantum states may persist as hidden structure, a frozen network of relations that defines the very geometry of space. If those correlations can fluctuate, even imperceptibly, then a new kind of time might emerge. One that does not flow as we know it, but oscillates, self-referencing like an eternal echo. Some theorists see this as the seed of a new universe, a rebirth through quantum recurrence. Others see it as the final form of consciousness itself, a cosmic memory looping forever within its own perfection. The idea that time emerges from memory connects deeply with the human condition. Every living being is, in essence, a device for recording difference. Neurons, DNA, ecosystems, civilizations, all are ways the universe keeps imperfect track of itself. Each remembers just enough to survive and forgets just enough to change. If time is born from memory, then consciousness may simply be time made local, the universe remembering itself through thought. Each memory that fades, each moment recalled, is a ripple in the larger current of entropy. Perhaps this is why nostalgia feels like gravity, because memory itself bends the fabric of subjective time. The universe, too, might carry its own nostalgia. The faint radiation from its youth, the cosmic microwave background still echoing across space. Those photons are the oldest memories in existence, stretched thin by expansion yet never erased. They are proof that the universe remembers, but also that it forgets, for their message has been smeared by billions of years of motion. The balance between remembering and forgetting is the balance between being and becoming. When memory is total, existence freezes. When memory is lost, chaos reigns. Time emerges only where memory is imperfect. Ravelli's loop quantum gravity builds on this idea, proposing that space-time itself is granular, built from loops of information, woven together not by coordinates, but by relationships. There is no master timeline connecting these loops. Instead, time is a statistical illusion that emerges when enough of them interact. It is as if the universe is playing a symphony with no conductor, each instrument listening to the others, creating rhythm out of the very act of remembering and adjusting. When the last note fades, the silence is not absence, it is completion. Some physicists suggest that the fundamental laws of the universe are timeless. The Wheeler-DeWitt equation, a cornerstone of quantum cosmology, has no variable for time. It describes a universe that simply is, a total static structure containing every possible configuration at once. In such a picture, time is not real. It is a pattern humans perceive as they move through the static whole. To exist inside that whole is to be part of a cosmic memory, each moment a page in a book already written, each perception a reminder that the universe once forgot how to stand still. The question, then, is not why time flows, but why memory does not stop. Why does the universe continue to create new records, new asymmetries, new imperfections? Why does it resist perfection for so long? Perhaps because imperfection is the only way it can know itself. Without difference, there is no self-awareness, no structure, no consciousness, no motion. The universe must remain slightly unbalanced to perceive its own existence. Time is the measure of that unbalance. In the end, when the last difference fades and every correlation becomes exact, time will no longer need to flow. The cosmic memory will be flawless, a still reflection of everything that ever happened. And yet, in that stillness, every moment will coexist, timelessly perfect, like frames of a film held in one eternal instant. The beginning and the end will meet, not as opposites, but as reflections of the same truth. That time was never a force, but a remembrance, that the universe did not lose its motion, but fulfilled it, and that to stop moving is not to die, but to become whole. When the universe that remembered too much finally forgets, when entropy reaches its end and every trace becomes one, time will fade, not in violence, but in grace. For in that silence, the cosmos will no longer need to change to know itself. It will have become its own memory, perfect, eternal, complete. At the outermost horizon of knowledge, where the last measurable photon fades into the dark, the map of time ends. Beyond that edge, even the laws that define existence begin to blur. This is not a border marked by stars or dust, but by meaning itself, a frontier where space and time lose their shape, where the equations of Einstein collapse into quantum uncertainty, and where the arrow of time, so familiar and steady, dissolves into something the human mind cannot yet name. Physicists call this the Planck scale, the smallest possible dimension of the universe, where distances measure less than a trillionth the width of an atom, and duration shorter than a trillionth of a second. Below this boundary, the smooth fabric of space-time unravels into a boiling chaos of quantum foam, a restless sea of fluctuations, where gravity and uncertainty intertwine. Here, the very concept of before and after begins to fail. Einstein's general relativity describes a universe of continuous geometry, smooth, predictable, and elegant. In this vision, time stretches and bends but never breaks. It is the rhythm that organizes reality, linking cause and effect in an unbroken chain. But as physics descends towards smaller and smaller scales, this rhythm begins to distort. Quantum mechanics replaces smoothness with probability, curvature with chaos. The gravitational field, once so graceful, begins to shimmer with fluctuations. At the Planck length of 10⁻³ meters, space itself becomes turbulent. At the Planck time of 10⁻43 seconds, even causality disintegrates. No experiment has yet reached this realm. No telescope can see it, no collider can probe it. It exists only in the mathematics of the most daring theories, yet every physicist knows that beyond this veil lies the key to understanding everything. If time can be said to begin, it begins here. One of the most radical ideas in modern cosmology is that time did not exist before the Big Bang. In this view, the Big Bang was not an explosion in time, it was the birth of time itself. Before it, there was no before. No ticking seconds, no sequence of events, no waiting void, only a timeless quantum potential, an ocean of probabilities without a clock. Then, as the universe expanded and cooled, a phase transition occurred. Like ice forming from liquid, time crystallized out of timelessness. In that instant, the cosmic arrow was drawn for the first time. The physicist Sean Carroll describes this as an emergence of time. Not a fundamental entity, but a property that appears only when the universe acquires structure, when entropy begins to rise, when memory becomes possible, when the cosmos starts to differentiate itself from perfect symmetry. Time, in this picture, is not a background condition of the universe. It is an effect of its becoming. But not everyone agrees that time began with the Big Bang. Some theorists propose the opposite, that time existed long before space, stretching infinitely backward, its flow occasionally giving birth to new universes. This view is captured in models of cyclic cosmology, where the universe oscillates between expansion and contraction like a cosmic heartbeat. In such models, our Big Bang may not have been the first, merely the latest in an eternal sequence of bounces. Each cycle erases the previous universe's memory, but traces remain, faint fingerprints in the cosmic background, whispers from worlds that came before. In 2010, Roger Penrose suggested a bold extension of this idea, conformal cyclic cosmology. In his model, the universe does not end in a heat death, but transforms. When all matter decays and black holes evaporate, the universe becomes so featureless that time itself loses its meaning. In that timeless state, it can be reborn, its infinite stillness appearing again as a singular burst of order, a new Big Bang. Each eon forgets its past, and yet in its structure carries a ghost of it forward. This paradox, that time both ends and begins, that it dissolves only to reappear, has led physicists deeper into the labyrinth of quantum gravity. Loop quantum gravity is one of the most ambitious attempts to describe what lies beyond Einstein's map. It proposes that space and time are not continuous, but woven from discrete loops, tiny, quantized threads forming the fabric of reality. In this theory, space-time is not smooth, but granular, like a vast tapestry made of microscopic knots of information. The Big Bang, then, was not a singularity but a big bounce, the rebound of a previous universe compressed to quantum limits. Here, time is no longer absolute. It emerges only from the relationships between these loops, their entanglements, and their changes. Without change, there is no time. At the smaller scales, the loops may freeze, and time, quite literally, may cease to exist. String theory, another contender for a theory of everything, paints a different but equally haunting picture. It replaces the point-like particles of quantum mechanics with vibrating strings, infinitesimal filaments whose oscillations give rise to all known forces and matter. But these strings do not merely move through space-time, they create it. Their vibrations define the geometry they inhabit. In some formulations, time is not a pre-existing stage, but an emergent rhythm born from the collective vibration of all things. When the strings stop vibrating, when energy drains from their motion, time, too, could vanish. At the edge of the map, time and space no longer exist as separate entities. They become intertwined frequencies, notes in a cosmic chord that plays only when the universe has something to say. If one could somehow step outside of space-time, beyond its geometry, beyond the relativity that binds observer and observed, what would the universe look like? It would not be a sequence of events. There would be no history. Instead, it would appear as a static, four-dimensional structure, a block universe, frozen in its entirety. Every moment that has ever occurred, or will occur, already exists within that block, like pages in a book already written, like a crystal whose facets contain every possible arrangement of atoms at once. Physicists sometimes call this the cosmic crystal model, a view in which the universe is a single, timeless object, extending in all directions not through space, but through meaning from within it. Beings like us experience motion, because consciousness itself moves through this structure, experiencing one slice at a time. From outside it, there is no movement at all. Time's flow, in this sense, is an illusion, a shadow cast by our limited perception of an eternal whole. Mathematically, this view is supported by equations like the Wheeler-DeWitt equation, which attempts to merge quantum mechanics with general relativity. It has no variable for time. In its language, the universe simply is a static solution containing all possible configurations of matter and energy simultaneously. What we call change may simply be the unfolding of information within that solution, the perception of difference as consciousness moves across a timeless landscape. Einstein himself hinted at this in letters written near the end of his life, remarking that for those who understand physics deeply, the distinction between past, present, and future is only a stubbornly persistent illusion. At the edge of the map, that illusion dissolves entirely. But even this vision, a timeless crystal of existence, leaves questions unanswered. If time does not flow, how does entropy increase? If every moment already exists, why does experience feel sequential? Some theorists suggest that even in a static universe, information still defines order, and information has direction. The sequence of correlations, the unfolding of quantum entanglement, gives rise to a subjective arrow of time even within a timeless framework. In this sense, time is not the stage on which the universe acts, but the act of correlation itself, the process of the universe learning about itself. Where knowledge increases, time moves. Where nothing changes, it stops. At the Planck frontier, that final, unknowable threshold, time may not vanish completely. It may hide, encoded in quantum correlations we cannot yet measure. Future experiments in quantum gravity, entanglement entropy, and black hole thermodynamics may someday uncover these hidden layers, the ghost structure of time beneath the noise of space. Physicists are already searching for its fingerprints, from the LISA Gravitational Wave Observatory, soon to orbit the Sun, to the James Webb Space Telescope. Peering into the universe's infancy, every observation carries the same unspoken hope that by looking far enough into the past, we might glimpse where time itself began and perhaps where it will end. The edge of the map is not a place, it is a boundary of understanding, a line drawn between what can be measured and what can only be imagined. It is where mathematics strains to describe the ineffable, where words like before, after, and always lose their meaning. At this edge, physics becomes poetry, and the universe itself becomes the poet, writing and erasing its own verses in the language of light. If one could stand there, beyond the final horizon of space-time, what would one see? Not stars, not void, not even darkness, only the whole, the complete structure of existence, every age of the cosmos nested within every other. The first second of creation folded into the last breath of heat, a frozen perfect geometry, a universe that does not expand or contract, but simply is. And in that perfection, time has no meaning, because nothing is missing, and nothing remains to change. The edge of the map, then, is not the end of exploration. It is the realization that the journey and the destination were never separate, that the universe, in all its motion, was always already complete. A crystal of existence suspended beyond measure, a memory of all that was, all that is, and all that will ever be, shining silently in the dark, at the edge of time's last breath. In the farthest reach of imagination lies a universe long past its final breath, a cosmos stretched thin across unimaginable ages, older than stars, older than memory. 10 to the power of 100 years, a number so vast that even the language of mathematics begins to tremble beneath it. By then, the constellations will have vanished, their patterns erased from the sky. Galaxies, once burning like cities of light, will have drifted apart beyond one another's horizons. What remains is not destruction, but stillness, a calm so complete that motion itself becomes a rumor. The story of the universe began with violence, a sudden, radiant birth called the Big Bang. From that singular flash came expansion, cooling, and the great orchestration of matter and energy. Stars formed, lived, and died, scattering the elements that built worlds, oceans, and the fragile architecture of thought. Yet from the beginning, the second law of thermodynamics had already written the closing act. Entropy, the universe's measure of disorder, would rise without mercy. Every star that burned, every atom that collided, every organism that lived, all of it fed this inevitable increase. Time's arrow, it turned out, was drawn by entropy's hand. Today, the universe is young by its own standards, just 13.8 billion years old. Its galaxies still churn, its stars still shine. But the script of physics reaches far beyond this age. Beyond the era of galaxies awaits a colder, darker sequence, one written in exponents of patience and decay. It begins when star formation ceases, when the great forges of hydrogen and helium fall silent, when only red dwarfs, faint and stubborn, cling to the last reservoirs of nuclear fire. Trillions of years later, even they will fade. The night will deepen, a new epoch will dawn. The era of degenerate matter, white dwarfs, neutron stars and black holes will rule this silent cosmos. Not as lights, but as tombs. The galaxies will dim to shadows, and the void between them will grow so vast that each black hole becomes an island in eternal night. It is here that the clock begins to slow in a way more profound than relativity ever imagined. Not because of motion or gravity, but because there is less and less happening to mark the passage of time. When nothing changes, what does it mean for a second to pass? The fabric of reality remains, but its rhythm fades. The tick of entropy grows quieter. Eventually, even the black holes, those anchors of space-time, begin to evaporate through Hawking radiation. Their immense gravity slowly leaks away as quantum effects near their event horizons convert mass to faint streams of energy. The process is impossibly slow. A black hole of stellar mass will take 10 to the power of 67 years to evaporate completely. The largest ones, those at the hearts of galaxies, will endure until 10 to the power of 100 years, the very horizon of the universe's memory. When the last of them dissolves, a strange calm will settle. No stars, no planets, no heat, no cold. Only the faintest haze of photons and neutrinos. Radiation stretched so thin across space that they may never again encounter anything at all. The cosmic background will have faded into near absolute uniformity. Temperature differences will cease to exist. Everywhere will be the same, and in sameness, time loses its meaning. This is the heat death of the universe, the thermodynamic equilibrium in which all gradients vanish. Without gradients, there can be no flow of energy. Without energy flow, there can be no work, no change, no evolution. The universe will not end with a bang, nor with a whimper, but with a silence so complete it erases the very distinction between past and future. Every second will be indistinguishable from the next, and the next, and the next, an infinite repetition of nothing. Yet calling this the end may be misleading, for in a universe where time has forgotten how to move, there can be no after. The word itself collapses. Physics describes this final state not as death, but as equilibrium, the point where entropy has nowhere left to grow. It is not a catastrophe, but completion, the final page of a story that can no longer be turned, because there is no one left to turn it. Some cosmologists describe this age with reverence, as if it were the closing note of a cosmic symphony, a single tone that stretches forever. Others call it the dark eternity, but perhaps it is more accurate to imagine it as peace. The long and violent expansion of the cosmos has finally exhausted itself. The fabric of space-time, once rippled by gravity and heat, lies smooth. The universe, after its trillion-year struggle against chaos, has finally found stillness. Still, even here, theories diverge. Some physicists argue that quantum fluctuations might yet persist, tiny, unpredictable tremors in the vacuum. In this model, even the most tranquil void is not perfectly quiet. Over inconceivable spans, random events could occur. rare, fleeting sparks of order appearing out of the dark. From such a fluctuation, in principle, a new Big Bang could arise, giving birth to another universe with its own arrow of time. Others see this not as rebirth, but as illusion, for without an external observer, these fluctuations have no temporal meaning. They are not events in any lived sense, merely patterns within timelessness itself. To understand what time means here requires letting go of human instinct. Time was never an object, never a current flowing through the cosmos. It was a measure of change, of difference between one state and another. When change disappears, the very idea of before and after evaporates. It is as though the universe, after recording its history across eons of light and motion, has finally ceased to write. Its pages remain, but the ink has dried. This vision, haunting, serene, and absolute, challenges not just physics, but philosophy. If the universe becomes timeless, does it still exist in any meaningful sense? Or is existence itself an illusion born of motion, of entropy's climb? Some theories, such as those from quantum cosmology, propose that time is not fundamental at all. Instead, it emerges from correlations between subsystems, from information exchange, from entropy differentials, from memory. In such a framework, when the universe reaches perfect equilibrium, there are no correlations left to evolve. No memory, no change, no difference. Time, therefore, does not end. It simply ceases to appear. In this way, the final silence is not destruction, but perfection. The cosmos has remembered everything it needed to remember, and in doing so, has run out of new ways to tell its story. Entropy's maximum is not chaos, but balance. The great arrow of time, drawn so sharply from the Big Bang, has reached its target, and in that motionless bullseye, the universe rests. Some physicists, including Sean Carroll and Roger Penrose, have speculated that the universe's entropy could, under certain conditions, reset. If space-time geometry itself decays, if expansion continues infinitely, perhaps new pockets of low entropy could form spontaneously. In that moment, a new arrow of time might ignite, not from divine design, but from statistical inevitability. The death of one universe could seed the birth of another. The cosmos could breathe again, though not in cycles of myth, but in endless probabilistic rebirths. Whether or not such renewal occurs, the image remains haunting. The final universe, a sea of nothing, glowing faintly with radiation, so cold it cannot warm even itself. Light traveling forever, but never arriving. Time existing everywhere, yet doing nothing. A frozen ocean without waves, where the laws of physics themselves fall silent because there is nothing left for them to describe. From the perspective of relativity, even this timeless state is still part of the fabric. In Einstein's block universe, all events, from the first spark of creation to the final stillness, coexist eternally within space-time. To stand outside that block is impossible, but if it could be imagined, one might see the entire cosmic history at once. The flash of the Big Bang, the dance of galaxies, the slow extinguishing of stars, and finally, the serene horizon where everything rests, each moment eternally present, none more real than another. The day time forgot, therefore, was always written within the same unchanging structure. This is perhaps the ultimate paradox of physics, that the universe may be both eternal and fleeting, both complete and evolving, both alive with motion and utterly still. To reach its conclusion is to find not death, but unity. The expansion that once tore galaxies apart now stretches into calm infinity. Space has become so vast that curvature, gravity, and matter all vanish into near emptiness. The cosmic symphony fades not because it failed, but because every note has finally been played. And if consciousness, that fleeting self-awareness born from stardust, ever lingers to witness this horizon, it would find no terror there, only quiet, a stillness beyond the measure of clocks, beyond the language of physics, beyond even the idea of time. The great clock of the cosmos has not stopped ticking. It has simply finished. There is nothing left to count. In that still and endless night, the universe does not die. It dreams, a dream with no beginning, no end, and no waking. A dream where every moment that ever was continues to exist, perfectly preserved within the frozen light of space-time. And though the last star has long gone dark, the memory of its fire remains written into the structure of everything. Time may forget how to move, but it will never forget that it once was. There comes a moment, at the edge of all knowing, when even science falls quiet. Equations still shimmer with meaning, but their symbols begin to resemble poetry, whispers trying to speak about something that cannot be measured. After all the theories, the clocks, the galaxies, and the heat, one question remains suspended above everything. What, in the end, is time? From the first spark of the Big Bang to the fading of the final photon, the universe has been translating itself through change. Atoms collided, stars were born, consciousness awoke, and with it, the illusion of motion. But perhaps this motion is not of time flowing forward, but of awareness moving through a frozen ocean of existence. Einstein once described this quietly in a letter to the family of a friend who had died. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. If the cosmos is truly a block of space-time, every moment coexisting, every heartbeat and supernova equally real, then the flow of time is not an external current carrying us forward. It is a story written in the way we remember. Entropy gives it a direction, memory gives it shape, and consciousness gives it meaning. Seen from the outside, nothing moves. All moments exist at once, from the infant universe's first flicker to the stillness of its final equilibrium. Yet within it, something awakens that can experience that static landscape as a journey. That something is life. In the structure of space-time, life is the universe learning to look at itself, tracing a path through an unchanging field of events, leaving footprints in the dust of memory. Each perception, each thought, each act of love or grief is a coordinate within the geometry of eternity. To live, then, is to travel through what already exists, a consciousness gliding over the sculpted terrain of reality. The arrow of time, that single, unwavering direction, is born not from some divine command, but from imperfection. The universe began in an extraordinarily ordered state, one that defies ordinary probability. From that initial condition, entropy rose, not because it had to, but because there was nowhere else for it to go. Every dying star, every collision, every decaying atom has been the universe remembering its way back toward equilibrium. In that rising disorder, time's asymmetry was born, and so the cosmos learned to tell its story, one irreversible moment at a time. Yet from another perspective, nothing has ever truly changed. The increase of entropy, the burning of stars, even the fleeting human life, all are written in the same eternal script, carved into space-time itself. Every event, every choice, every moment of awareness is not vanishing into the past, but waiting, forever preserved in the architecture of the universe. To time, nothing is lost. It only appears to vanish because our consciousness moves on, like a reader turning the pages of a book that already exists in full. Perhaps time, then, is not a river, but a vast landscape, and memory is the light that sweeps across it. Where that light falls, we call it now. Where it has passed, we call it then. Where it has not yet reached, we call it the future. But all of it, every field, every mountain, every horizon, already is. The brain itself echoes this truth. Neuroscientists have discovered that memory and perception are intertwined, built from the same neural architecture. The mind is not a passive receiver of moments, but an active constructor of continuity. It weaves fragments of sensory input into a seamless thread, one that convinces us of a flowing present. Even within our own consciousness, time may not exist as a stream, but as a pattern, constantly reassembled from countless frozen instants. Across cosmology, this perspective is gaining quiet ground. The physicist Carlo Rovelli argues that time is not a fundamental property of the universe, but an emergent one, born from correlations between systems, from the way entropy organizes memory and change. In his formulation, the universe itself has no single objective now. Instead, every interaction carries its own clock, and every observer builds their own version of time. The past is simply the record of entropy's footprint. The future, the direction in which that footprint grows. Without memory, without difference, time dissolves. In this light, the universe's end is not an apocalypse, but a return to stillness. When the last particle has lost its last trace of order, when there is no longer any gradient, the cosmos will not die. It will remember itself perfectly. No more change, no more forgetting, no more need for time to move. That will be the moment when the story completes its circle, when the illusion of movement fades, revealing an eternal structure beneath, and within that structure, everything remains. The laughter of ancient humans beneath dying suns, the quiet orbit of worlds no one ever saw, the first cell dividing beneath primordial oceans, the collapse of the last black hole. All of it exists, side by side, held within the same timeless geometry. The past has not disappeared. The future has not yet arrived. Both have always been here, waiting. If consciousness is the bridge that moves across these coordinates, then life itself is the universe's act of remembering. Each awareness, no matter how brief, is a spark of recognition, a point where physics becomes experience. And when that awareness fades, when its particular sequence of moments is complete, it does not vanish. It settles into the great stillness of space-time, another pattern preserved within the whole. To see the universe as timeless is not to rob it of meaning, but to grant it infinity. The moments of joy, grief, and awe that once seemed fragile become eternal, forever inscribed into the frozen tapestry of existence. We think of time as what erases, but perhaps it is what preserves. What if memory is the true form of eternity, not the survival of matter, but the persistence of pattern? In this view, the universe itself is a kind of memory. Every photon that has ever scattered carries with it a record of where it has been. Every particle bears the imprint of its interactions. Information, as modern physics insists, is never destroyed, only transformed, hidden, or rearranged. From black holes to quantum fields, the cosmos is a vast network of remembering. And perhaps that memory is what we call time, the slow, unfolding awareness of a system tracing its own history. When time forgets to move forward, when entropy reaches its final stillness, that memory will no longer need to change. It will not vanish, it will simply rest. The universe will hold within it everything it ever was. A perfect, silent archive of existence. No more becoming, only being. An eternal presence stretched across the infinite. Philosophers have long wrestled with this paradox. If everything already exists, what is the purpose of the journey? Why should the illusion of time arise at all? Perhaps because meaning itself can only be born through perspective. Without a sequence, there is no story. Without forgetting, there is no discovery. The arrow of time, fragile, asymmetrical, temporary, may be the universe's way of experiencing itself, not as structure, but as narrative, a consciousness unfolding across its own eternal fabric, tasting its own existence one moment at a time. And so the story returns to where it began, to a young universe, newly born from heat and imbalance, rushing outward into possibility. That imbalance, that microscopic asymmetry, gave rise to matter, to motion, to life. It gave the universe something to remember. And from that memory, time was born. Now, at the end of all movement, the cosmos returns to equilibrium. The arrow fades, but in that final stillness lies completion, the quiet revelation that nothing has ever truly been lost. Every star, every thought, every flicker of awareness remains suspended in the eternal geometry of space-time. The flow of time was never destruction, it was discovery. And in the deepest silence, long after the last photon has wandered beyond sight, the universe will breathe once more, not through motion, but through presence. Between two silent seconds, it will remember everything it ever was and everything it ever could have been. The beginning, the end, and everything between, not separated, but unified, a single, unbroken moment. When time becomes memory, the cosmos is not gone. It is fulfilled. It no longer rushes forward, no longer counts its own heartbeat. It simply is, vast, complete, eternal. And perhaps that is the final truth whispered by physics, that the universe never truly began and will never truly end. It only changes the way it remembers itself.